Okay, so we are starting into our last little section of the course, thermodynamics. If I were to look at my notes right now, I would say that it's slightly thinner than all the other sections, even the first one, which is kind of thin on my notes to begin with. And that's because in many respects, there's only a couple things to go over with thermo. But when I say that, of course, it's when I first started teaching this course, and I remember Dr. Fall saying to me, we're only doing 3 things. We're doing rate laws, equilibrium, and thermo. I'm like, that's like a couple weeks worth of stuff. And he just chuckled. And as I told you guys at the beginning of this, only 3 things. And we've only done 2 of them in like 10 or 12 weeks. So it will take a little bit of time, mostly because we're going to be tracking down a lot of math. So one of the things that is going to be very important is to keep your frame of reference, to keep track of negative signs, keep me track of negative signs. Believe it or not, I also lose sight of them. That's probably the most common mistake people make in this is the negative sign. So it is going to be pretty easy to set them up as long as we methodically go through the quote, what is going on. Only this quote, what is going on, is a whole lot easier to keep track of than the previous ones, the equations for equilibrium. So with that, I need to get up my participants list because that gives me a frame of reference as to how far I can go over. And let me get you guys situated here. Where's my thing? Get you over there. Drag you down so I can see a few. Make sure some of my go-to peeps for questions are still around. All right. Let's talk about thermodynamics. Normally, right about now, there's this really cool clip from The Simpsons where Homer says, in this house, we obey the laws of thermodynamics. But I can't show it to you guys. All right, so let's talk about thermo. Thermodynamics. As the name might imply, thermo means heat, and dynamics means moving. So what we're talking about is the flow of heat or energy from hot to cold. So this is the flow of energy, which a lot of people will go ahead and say heat. I don't like that because they'll also say that heat is the flow of heat, which is really weird. So I like to call it the flow of energy or heat from one thing to another. And we should note that it always goes hot to cold. That is the definition, how we define the energy transfer that is going on in thermodynamics. The frame of reference is always hot to cold. That may seem intuitive, but it is noteworthy to put it down because we all have to agree how we're actually going to view this heat transfer, this exchange. Okay, there are 3 things that contribute to thermodynamics. So 3 things that contribute to thermodynamics. Ooh, one of my longest titles there. These 3 things are delta H, which is called the change. You guys will recognize that delta. The change in something called enthalpy. Now, the enthalpy is just a way of talking about, specifically in a chemical reaction, the difference between the energy it took to break the bonds and the energy that we get out when they reform. So this is the difference in energy difference in energy between breaking bonds and forming bonds. Now, you might remember from the Wayback Machine that we said whenever you form bonds, you release energy. But one of the things that is often left out, especially when I tell you at lower levels, is often to form new bonds, you got to break the previous ones. So we say something like hydrogen and oxygen make water. That's a very exothermic reaction. It gives off a lot of energy. But you can't just put hydrogen and oxygen in a room and say, go for it. You have to actually do something. And that usually comes in the form of a spark. And so the breaking bonds is the energy that you put in, and the forming bonds is the energy released.
Forrest, do you mind scrolling back up really quick?
For my Johnny come lately, or should I say Kyra come lately? I'm just messing, Kyra.
Thanks.
Not a problem. Now, enthalpy is essentially the intrinsic energy stored up in these chemical bonds. So, so when we talk about enthalpy, it's sort of the inherent chemical energy that every compound has. It should be noted that if the delta H is positive, we call that exothermic. Oh, sorry, endothermic. Sorry. Glasses, work up close. Put your notes closer. There we go. Delta H positive is endothermic, which means it's going to cool down. If the delta H is negative, it is exothermic, which means it heats up. Oftentimes the endothermic might look something like, some people put this here, they'll say something like heat plus A plus B goes to make C, so you have to pump energy into it. Whereas exothermic might be A plus B goes to make C, and a bunch of heat is released. So when we talked about equilibria, and we said that there is a heat component to these, and you can change the equilibrium constant at any given temperature, that could be looked at as either an ingredient, a reactant, or a product. And whether you increase or decrease the temperature, you could shift equilibria by treating it as either a reactant or product and moving the equilibria that way. So this is just another representation of how sometimes people will write these in chemical equation, especially if they're talking about thermodynamics. The other way is, of course, if you remember, you can put the little delta sign above to indicate that heat is getting put in. Okay, the other thing we have is entropy. So the change in S, this is called the change in entropy. And basically, this is a measure of the disorder of a system. So it's a measure of the disorder of a system. And remember, system is what you're looking at. So when we talk about a system, we need to remember it's whatever we are looking at. So if we're looking at a solid melting, we're talking about what is happening to that thing. If we're talking about whether or not some water is freezing. That's what we're looking at. If we're looking at us versus the chemical reaction, now this is something that is interesting, and I should note for all my engineers out there, especially if we've got Tristan there and Gherkin. Did Gherkin show up today? My little chemical engineer? She did not. So pure scientists and engineers actually often think about these things in a different manner. Pure science, chemists and stuff, we often think about the system as being what we are, as in the chemical reaction. Engineers try to say, yeah, but what's it going to do for us? And say they sometimes think about it in what some people might call a reverse order. It's all about your frame of reference and whether or not you're getting what you want out of the thing. You'll see as we do some more problems. Well, any problems, here we go. It should be noted that if the change in entropy, so if the change in entropy is positive, it becomes more disordered. And if it is negative, it becomes more ordered. And again, you could think of this in sort of a physical sense of freezing water makes those water molecules locked into more of a framed network, creating more order. Melting it allows those water molecules more freedom, more places to move around. It becomes more disordered. The last thing we have is actually interesting that they call it the third thing, because it's really just a combination, and that is something called delta G. And this is called the Gibbs free energy. And this is often called the energy available to do work. Now, what that really means is, it is, if you are going to do some sort of reaction or look at a system and figure out what's going on, at the end of the day, you can look at the energy before and after, and great, it released a bunch of energy and it got hot. Okay, and maybe it got more disordered. Okay, that's great. But at the end of the day, what is it that you and I, as greedy, selfish human beings, what can we do to make all that energy work for us? And that's where the Gibbs free energy comes in, because we're going to find out that there is oftentimes a competitive effect between what happens when you break and remake bonds, and then what happens with that entropy. And it turns out that there is a temperature dependence on this. And it is that the delta G is equal to delta H minus T delta S. So you have a temperature coming in here, and that temperature will actually start messing with, either in a positive way or a negative way, depending on your point of view, how much work we can get out of this system. Now, it should be noted that when we talk about enthalpies, we talk about it being endothermic or exothermic, heating up or cooling down. Entropy is more ordered or disordered. Delta G actually talks about what I spoke of probably in the first day we ever got together. And that is delta G, if it is negative, that means that the reaction, oops, I need to put this in blue, is spontaneous as written. And that also means that if the delta G is positive, the reaction does not occur. As written.
And that's on its own, correct?
The reason why I say I hesitate on the on its own because you always have to give reactions a push, okay? So you can't, like I said, you can't just put hydrogen and oxygen in a room and say, go at it and make water. When I was at American River College and I had access to hydrogen and oxygen gases, I would make stoichiometrically matching balloons with two parts that by volume. And I walked around with my little balloon and everything, and I happened to have a candle at the end of a 2-meter long stick, because while I do nothing, that balloon just floats in the air. It's all nice and handy. It's great. But as soon as I took my 2-meter long stick and put that fire to it, a rather large explosion occurred, invoking the president and the chief of police to come over and have a couple of words with me. So that is a true story. So when we look at this, we have to keep in mind that it's not that we're saying it's spontaneous just because you decided to get the two things in the same place. It's spontaneous once you decide to start the reaction going. So keep in mind everything, and in fact, you know, if you want to get down to it, it really is reminiscent of. Let's see if I can get that up out of my way. Maybe I can just pull it down to the bottom. If I go back to this, you guys might remember this guy. So we had this little plot that went whoop. You guys remember this?
Yes.
Yeah.
Right, we had our activation energy. And we had our reactants and our products. Which meant that at the end of the day, we had an energy difference. So when I say, like, yes, they want to go, basically, we are looking at a combination of the energy before and the energy after. Now, this graph is misleading in some respects because it's not taking into account the entropy, although you can plot Gibbs free energy plots like this. But what I'm pointing out is that if you can get energy out, it's probably going to want to go. So does that make sense? Why I kind of hesitated there, Dallas?
Yeah, I think I get the idea.
Okay. I want to point out a few other things before we start talking about these individually. So we have the three things that we're gonna look at. We're gonna look at delta H's. We're gonna look at just the change in the breaking and reforming of bonds, and what does that mean for the energy out or the energy we might have to put in to actually making it work. We're gonna look at what happens to the entropic change, whether making the system more disordered or more ordered will affect this guy, the Gibbs free energy, and how much to do work. I do want you to notice that if we start messing around with the temperature, right, the more we have our temperature, the more we start invoking the entropic effect, whether it's to our favor or not, in the overall ability to put this system to work, to move a piston or transport some ions or something like that. Anything that allows you and I to extract the work that chemical reaction is doing into something that you and I want it to do. And we'll see that when we finally get to electrochem and where we try to actually get the electricity out of all this sort of stuff. I do want to point out too here, as far as life is concerned, equilibrium is death. I told you it would get grim toward the end of Chem 121. Rate laws tell us how fast. Equilibrium tells us which way. Thermo is going to tell you, did it happen or not? And if you think about thermodynamics, you have to have some sort of driving force. Something has to be hotter if we're just talking about heat, the movement of that energy. If something has to go from hot to cold, once they are the same temperature, there is no driving force to do anything. That's equilibrium on a temperature scale or on a temperature metric. Once you are at the same temperature, nothing is moving. There's no driving force. That system, as it were, is dead. To get it slightly a little more upbeat, the reason why you and I eat every day is to stay alive. Because what do? We now front load our reactants, the energy, the food, the whole dairy, you name it. Our body now uses that to do its reaction to extract all the heat. If you guys remember, human beings are just one little organic battery, right? We're just there to make energy. If you stop eating, you run out of stuff to use, you will reach equilibrium, AKA you're gonna die. So in a less macabre way of looking at it, you know, when a dead battery occurs, we all have batteries. That means there's no more ions to complete the circuit. There's no driving force. At equilibrium, delta G is so what do? We push things out of equilibrium onto equilibrium, and that's what's going to allow us to monopolize that delta G. So we push systems out of equilibrium, watch them go back, and extract that work. And again, dovetailing off of the battery thing, we go to rechargeable batteries. Is there an E in rechargeable? I think so. Oh, I don't think so. Well, you'll get it. So what do we do with rechargeable get in? What are we doing? We're putting energy into the system. We're forcing those ions to go back from the place they came. Let those ions flow back across, completing an electrical circuit. We extract that work and our phone works. If we fail to push it back out of that equilibrium, if we fail to move everything back to its original starting point, we will eventually reach equilibrium. Speaking of electrical energy, since we are talking about things in terms of volts and currents and things like that, it should be noted, by the way, this is normally a script E. I can't really do a script E very well. I will try to just do that sort of back end thing. But if you look in textbooks, they have a really nice scripted E for this. Negative NF E. And this term right here, as we'll see a little bit later, this right here is a scaling term. The number of moles of electrons and Faraday's constant. You guys may have heard of Faraday. And what this is it's a scaling factor. You take delta G, which by the way is in joules and energy, into E, which is in volts. Now, I know I'm going a little fast here, but check that out. We have a negative sign there. Because if you recall, we go back up here to the delta G. We said it is spontaneous, which means it wants to go. That means if delta G were negative and we have this negative, and negative times a negative is a positive, that basically turns into a positive voltage. Just so it's something that you and I recognize. And so it should be noted, of course, energy is positive, it is spontaneous. If it is negative, it does not occur. Now, before I move on and actually, well, we'll do one more thing, but before I look at that, I do want to point something out. I keep using this spontaneous versus does not occur, or spontaneous versus not spontaneous. Now, it's disingenuous to say that it doesn't work. Now, when I say that, I'm saying that the thing that we want to happen, is not occurring. But clearly, if we have, say, a negative voltage, and we've all probably worked with a voltmeter or something here throughout our lives or something, you'll find you have a negative voltage if you hook up the leads one way and a positive the other, and you go like, so you're telling me that like this battery doesn't work and then it suddenly works? Keep in mind that whenever we're talking about something being spontaneous or something not spontaneous or not occurring, what we are really talking about here is the thing we're looking at. So let me do a quick little note. Actually, I probably shouldn't do the line there. So I want to note spontaneous means that the reaction we want to see is occurring. Not spontaneous means the backward reaction is occurring. So now we're looking at. All right, there's like, my voice is choppy, is that true? It's not just me? Okay, thanks. I'm still
no.
choppy, huh?
Yeah, it goes in and out.
Okay, let me check something real quick. I'm checking my internet speed just to see. Gotta love being country folk. Oh, wow. I will this in mind. Hopefully, we'll have my voice less choppy in the end recording. Sorry about this, guys. All right. So before we do a problem, I also want to note this. Delta G is what we call an extensive property. This means it depends on the amount. So you might think of this as 2 tanks of gas, twice as far to drive. Delta G is extensive. It depends on the amount. More gas, bigger explosion, right? More dynamite, bigger explosion. E is what we call an intensive property. Now, an intensive property is the opposite of an extensive, so it does not depend on the amount. So when we say it doesn't depend on the amount, we can think of voltages, right? A AAA battery is 1.5 volts. A D cell battery is still 1.5 volts. So I don't care how big those batteries are, they both give the same voltage. Those are bigger, just means that these guys just means they last longer. Okay, the NF is what turns that extensive into an intensive. Okay, take a look at that first one. Let's take a look at enthalpy.
Forrest, can you scroll back up? You had frozen for like a little bit.
Oh, yeah, sorry. Sorry about that. A little more?
No, that's fine.
That's fine, okay. So as we look at this, and we'll come to the voltage thing will come at the end of this section. First, we're going to talk about H, then we're going to talk about S, then we'll talk about delta G, then we'll convert delta G's into E's. So don't get too hung up on the voltages yet. We got a few weeks.
Before
Yes.
the
Yes.
whole not spontaneous, meaning the backward reaction is occurring. Are we going to revisit that later and talk about more?
We're going to revisit that a lot, yes.
Okay.
So what I mean by that is, well, we already know. So I'm just going to write this down and then erase it, okay? So well, actually, I'll just do this. Hold on. Let's get rid of this. So Tristan asks, spontaneous versus not, okay? So here's what I mean. We actually already know this intuitively. We already know this. How do we know this? HAC. What does it do? Breaks up into H pluses and AC minuses. Okay? Now, it does that, and equilibrium says that not very much goes to the right, right? So when we said that, it mostly stays as HAC. So when we are talking about HAC, breaking apart, and it's actually even better with solubilities for solids here, we know that only some of it wants to break apart. Well, if we add more HAC, it has limited driving force to break apart. But add a bunch of H plus and AC minus, very big driving force. Man, my handwriting is awful today. Very big driving force to make HAC. So if what you wanted to do, Tristan, if what you wanted to do was say, hey, I'm going to put a whole bunch of HCl and sodium acetate into this container and let them just swim around as H's and AC minuses, if that's what you want to see, that ain't going to happen. Because thermodynamics says it would rather, equilibrium says, it would rather get together and go back to make HAC. If, however, you said, hey, I want to put these two things in there and watch them make the HAC, then you'd be like, oh, well, totally. We got a huge driving force to do what I want. So the thing that I'm looking at now, yes, that is what I want. And so when we say if not one way, then the other, it depends upon the conditions you are making, okay? And again, we'll revisit this, especially as we get further along to the voltages. We'll talk a lot about electrochemistry in terms of those things. So when we talk about the spontaneous, we're going to look and see the bonds before, the bonds after, and whether or not you have an entropy increase or decrease. All of these are going to tell you when you dump that in, is that going to want to go? So, I mean, look at the H's and the AC's. Right now, if you make them come back together, you technically put them in a more ordered place. Well, nature does not like that. Nature loves chaos. So you're saying, well, I want you guys to stick together. And like, we kind of really don't. So entropically, it doesn't want to do that. Enthalpically, it says, yeah, but the energy we're going to get rid of by doing this is worth that cost of being more ordered. And therefore, Gibbs free energy says, H's and AC's, yep, you're going to make HAC. And so if that's the system you wanted to look at, you're in good shape. If instead what you wanted to look at is dumping those ions in and saying, hey, why don't you guys just keep swimming? They're going to be like, no. So it's your frame of reference as to Is it spontaneous as you are writing that equation, as you are trying to make that reaction go? Yes or no? And if the answer is no, then it means actually the reverse is happening. What you wanted to happen isn't, but the opposite is happening.
So then why does any
Does
of
that
it
help,
stick?
Jake? So why does any of it stick? What do you mean?
Why does any of it stay as H plus and AC minus if the net thing is, make HAC and,
Well, because remember, rate laws say how fast, equilibrium says which way / how much. Thermo just says yes or no. And so when we say that there is a driving force for the H's and the ACs to get together, I'm also making a disingenuous argument there, Dallas, because it does depend upon the concentrations at which you want to do this. So we know that HAC doesn't really want to break apart. About only 1% of it wants to break apart. Well, so if we'll go back to Tristan, he says, look, I want to put in like 10 to the minus 6 molar H's and 10 to the minus 6 acetates. And we would have seen this had we been able to do the carbonic acid lab for equilibria there. Those are already at concentrations low enough that essentially they're fine swimming around. And so if that's the system he wanted to look at, then yes, they will go ahead and swim around. If, however, he decided to put a 1 molar H and a 1 molar AC minus into the solution, they'd be like, yeah, that's way too much. We'd rather be HACs. And since we loaded up the product side, we will race over to the reactant side. So this is, and that's why we put thermodynamics at the end, because it does incorporate a little bit of that equilibrium factor for rate laws. I mean, kinetic equilibrium. Just remember, I'm giving you another tool. This is no longer a nail. You are no longer a hammer. So we're going to start being more subtle with our tools. And again, I didn't want to delve too deeply into it just yet because there is a ratio of products to reacting force later on down the road, because it does involve which way does that equilibrium want to lie in the first place as to whether or not we have the correct driving force thermodynamically. Because you can make systems that didn't want to go if you just make the conditions right. So this is very much conditions dependent. Okay. So now I want to look at enthalpy. Because it really is just about the temperature or energy difference. We're going to look at that average kinetic energy both before and after. So this is the easiest to look at because we only have to look at a delta T. And remember, recall, temperature is the average kinetic energy of the molecules of the system. Okay, so we are looking at how fast are those things moving, both before and after. And you have to keep in mind, I'm just going to remind you, probably Dallas is the one I need to remind, even if you're solid, those molecules are moving, they're vibrating, they're jiggling as a solid. So just because we might make a precipitate doesn't mean there's not energy associated with them. So just reminding everybody, but just picked on you, Dallas, because I can. Okay, so I want to point out here that the equation looks like this. Delta H is equal to M CP delta T. There's also another version. Delta H is equal to N CP delta T. You'll notice there's a slight difference there. We should recognize N. N is in moles. M will actually be mass. So M is the grams. And CP is what we call the heat capacity. And this is given in joules per gram per degree Celsius. Actually, M I don't want to say is that. I want to say it's mass, which is in grams. There we go. That's how I wanted to do it. Now, we have the CP, or the heat capacity, and then we have the delta T. Of course, that's the temperature change. And that's going to be in degrees C or Kelvin, because remember, since it's a difference, they are the same. It doesn't matter. So a couple things I want to note as you look around for any of these stuff. I want to note if using NCP delta T, N is in moles, and CP will be in joules per mole Kelvin, or joules per mole degree C. So you got to remember that differences in Celsius and differences in Kelvin, it doesn't matter. And this whole idea of a CP, you may also see this if you have ever seen in high school. I'll go ahead and put the other note. Sometimes written as delta H equals MC delta T, and they leave off the P. They're basically using a blanket heat capacity and not telling you the ins and outs, but for my chemical engineers, there is C, CP, and CV. C is generic. CP is done at constant pressure. And that's the one we're going to be doing the most with, because we'll be working with open systems where any gases or the like, we will let them do whatever they want. If they want to expand or whatever, they can do that. But in some engineering applications, you don't do that. You want to actually capture that. And instead of using the volume difference, you use the pressure difference. And so you will see some heat capacities written in terms of constant volume. Now, as we look at this delta H, if we do no work, so when we look at delta H equals MCP delta T, if we don't do any work, if we keep all the stuff at the constant pressure and let the volume do whatever it wants to do, and we don't harness any expansions or contractions or anything like that, if we aren't actually doing any extraction of work, then this enthalpy will actually just be the energy or the heat that was transferred from one system to another. So when we look at this, if we don't do any work, we'll worry about doing work later. Delta H is Q, is just the heat of the system. And so this delta H, so delta H equals mCp delta T, is often written as Q equals mCp delta T. And this is the one that is probably most familiar. If you've ever taken a high school chem course, you may have seen Q equals mC delta T. And really what this is just going to measure is heat flowing from hot to cold, monitoring that flow of energy and trying to capture what does it end up doing. And we're going to be using this one right here quite a lot. So we'll get really versed in this guy right here. Now I have used a little q because that's going to be for any and all pieces. When people use a capital Q, they mean it for the overall end game of a system. So let's do a very quick and easy dirty example, well, actually clean because we're using a lot of water, that might resonate with you guys at least physically and might resonate with you guys conceptually if you've ever thought about doing this. So a quick conceptual to physical example. We're going to warm the pool. Oh, I'm going to put that in red. Okay, so if anybody here had a pool and a hot tub, if you had one of those, you may have said to yourself in an early spring day when the pool was still too cold to swim in, what would happen if I took all the hot tub water and just dumped it into the pool? Maybe it'd get hot enough to actually get in the pool and have a good time. So warm the pool. It is a cool spring day. And you want to go for a swim. But the pool is too cool. The pool is too cold. How about we dump the hot water from the hot tub into the pool to warm it up.
Well, how big's the hot tub and how big's the pool?
I'm going to tell you that because this is all about that internal energy of that, the stored up energy of that water as we have it, and it does matter. You know, like right now I have my coffee that is slowly getting colder and colder. I'm trying to keep it warm by topping it off with hot stuff. Well, I'm not pouring in very much hot stuff compared to the cold that's already there. Therefore, my coffee only gets to a certain temperature. We're going to do the same thing here with the hot tub and the pool. So Dallas wants to know, what are our amenities here? So we have our hot tub. I'm going to say it's a decent sized one. It's an 800-gallon hot tub, which I'm going to go ahead and tell you is 3,024 liters. And I'm going to keep it at a good balmy 104 Fahrenheit because that's how I think. But you'll probably want to know that that's 40 degrees Celsius. Now the pool, since the pool is cool, I'll do it in blue. The pool, let's say it's 20,000 gallons, which is 75,600 liters. Man, that's a lot of water. And it's a very cool spring day. That water is only 50 degrees, which is 10 Celsius. Okay. Now, this example, I'll warn you ahead of time, is incredibly simplistic. We're going to be able to do some things that we won't normally be able to do, but it's just going to get your feet wet, so to speak, into how to think about these problems. So keep in mind, if it looks like it's a way too simple thing, it is because I've set it up that way. But it is a way for us to get used to the how do we set this up scenarios. So heat lost by the hot tub water will be gained by the pool. Can we agree with that? I'm going to say yes.
Yeah, that's fine.
Now, we have to talk about conventions. What this that heat is going to be equal to the Q for the pool, because they can't equal each other just like that. One has to lose and one has to gain. So the convention is, if you are gaining heat, you're positive. So this is the convention. Your only job now is to make sure that when we start looking at more complex systems, you have to ask yourself, what is my system? What is important to me? And am I gaining or losing heat? Because that's the one that is going to be assigned the negative or positive, which means the opposite one will follow suit. Okay. So what we do now is we set this up. I like to say we have two things. We have our hot tub and we have our pool. Our hot tub is going to cool down. Our pool is going to heat up. And when we're talking about heating and cooling, we talk about this being the cooling down. All of this is going to be an MCP delta T, and the heating up is going to be an MCP delta T. We'll worry about our positives and negatives when we set it up. There'll be other equations for other types of transference of heat. Okay, so just because I'm being very meticulous here, you'll see why I'm constantly repeating myself over and over. So hot tub to pool. This is what we're looking at. One is cooling down, one is heating up. So this cooling down means we have a negative MC delta T for the hot tub is going to equal the positive MC P delta T for the pool. And I'll go ahead and do this. We'll do hot HT for hot tub, and we'll do pool for the blue. So if you only have black pens, one of the ways to denote this is to put your little bracket there and say, look, we're going to be talking about it in terms of those species. Set the Wayback Machine to the ideal gas from Chem 120. We did that when we were talking about the mercury system versus an alcohol system versus a water system. It's just a way of keeping track of which M is which CP is which temperature change is which. Now, again, I said that this is going to be a trivial example because we're going to be able to make some very clever simplifications. So I want to note here, simple example is simple. We get cool simplifications here. Oh. Now, the first simplification we can note is the CP for the hot tub is the same as the CP for the pool, right? We're looking at the heat capacity. We're looking at how much energy that takes to raise up 1 gram by 1 degree Celsius. That's what those units mean. Let me just remind us. I'll come right back down, Isa, for you to write that down. But when we talked about these units right here, if you look at them, it is how much energy to heat up 1 gram, 1 degree Celsius, or 1 Kelvin. So the more stuff, the more energy. The more temperature difference, the more you want to heat it up, the more energy. So these are all defined by how much energy for 1 gram and 1 degree Celsius on the heating. But since both are water, guess what? They have the same capacity. Because both systems are water. You're looking at the heat capacity of the pool water and the heat capacity of the hot tub water. They're the same. So that's kind of cool. So now what this means is we have the mass and the delta T of the hot tub is equaling the mass and the delta T of the pool. Well, we can make another simplification. Alice, what is that simplification?
The one that occurs to me is that the change in temperature, they're going to come to the same end temperature.
That's right. So that's not a simplification. That's where we're going to go. How would we figure out the mass of the water for the hot tub?
Isn't I don't remember, like 1 milliliter, 1 gram or something?
1 milliliter, 1 gram. Combine those to say?
1 liter, 1 kilogram.
Well, you could do that too, Dallas. That's not where I'm going. 1 gram per mil density?
Yeah.
Right? So if we were to convert each of these gallons / liters / milliliters to an actual mass, what's going to be the difference since they're all water? It's just going to be a scaling factor. So since they both use the same scaling factor to go from gallons to liters to grams, and since both systems are water, going from gallons to liters to grams, they both use the same scaling factor. So we can just use their volumes straight away. Right, if in going from these volumes to the masses, we're going to be multiplying both sides by the same scaling factor, we don't have to worry about it. So we can just use their volumes. Isa, did I go too fast? Are you okay?
No, I actually have a question.
Well, then why didn't you shout out the question?
Because I was finishing writing it down. Would viscosity have an issue with this equation?
Riddle me what you mean by viscosity. I like the fact you're thinking here.
Like, because you said like they're both water, but what if it was like, I don't know, oil to water or?
Those are different. Now, keep in mind something that I haven't said just yet, and I will if we have time for the next example, which I think we will. Everything has its own heat capacity. Everything has its own ability to suck up energy or release it, as it were, depending on which way you're going. And so whether you are metal or whether you are water, you will have your own specific heat capacity. Now, that doesn't have anything to do with the viscosity. Has everything to do with what the material is. And so
Okay.
I'm not really giving anything away here because we're going to talk about it a lot. Water has a stupid high heat capacity. It takes a veritable boatload of energy to heat up water. It's really, really difficult. But you already know this. If you took even a big, heavy cast iron skillet and you start, well, you know, for the 4 of you in here that cook, you know what I'm talking about. You put that cast iron skillet on the stove and you crank up the fire. It won't be very long before that pan is too hot to touch because it's pretty easy to heat up a metal. You put your water in there, you crank on the fire, and you could probably wait 2 or 3 minutes and still be able to stick your hand in there before it starts getting too hot for you to touch. That's because that water is busy absorbing and absorbing and absorbing that energy. And let me tell you, that cast iron weighs a whole hell of a lot more than that water. So it's not that like, oh, but you have a lot of water and only one little pan. No, iron's heavy, right? So it has going for it the fact that you have a lot more mass to try to heat up, and yet it's still heating up faster than that water. That's because water has a heat capacity of 4.186 joules per gram and Celsius. And looking back on my chart that I just printed out, hold on. Iron is 0.4, so 10 times less able to take that energy you're pumping in. So its temperature is going to rise real fast. So does that sort of tell you what's going on there, Isa?
Yeah, I think we would just have to do like a different example to get like a better visual.
We will. Again, this one is so stupid easy. It's just to get you, this example is all about this right here. Losing and gaining. Where does that negative go? Where does the positive go? And how do we finally solve for where do they end up? This example is nothing more than just getting our feet wet. Hashtag dad joke. All right.
Okay, thank you.
So we're going to use their volume straight away. So we know that we have 800 gallons. I'm just going to. Sorry. Was there a question?
Wait, so are we going to be using the gallons or the liters? Because
Did everything just cut out again?
yes, it did.
Back to the gallons because the numbers are smaller. It
All
won't
right.
matter.
Well, I mean, it kind of does because your conversions were wrong.
Right? What conversions?
Your gallons to liters, 800 gallons
Gross.
was a different
Are you
value.
going to
in
get
liters.
like all technical on me, Dallas? Are you?
I'm sorry, got choppy. I couldn't understand what you said.
What did you use as your conversion, sir? Because I went multiplied by 3.78 and got 3024.
I used Google. 3028.
To liters. Okay. And Google is probably using Yeah,
3.785.
you're majoring in minors. It won't matter. If I use the numbers and I use 3.78. Remember, when you're going from metric to English and vice versa, your sig figs matter because of the type of conversion you do. What I'm telling you, Dallas, is whether you use the liters I gave you or the gallons I gave you, it won't matter. It will come out in the wash.
All right.
So if you want to spruce up your numbers and use super accurate numbers, go right ahead. You'll get the same number as we do. So what we have here is 800 gallons. Now, temperature difference, we all remember, is the final minus the initial. And we have our pool, which is 20,000 gallons. And again, final temperature minus. Now, we know that this hot here is 40 degrees Celsius. This one actually matters, Dallas. We can't use Fahrenheit because, well, I guess you could, but you don't want to. You want to stick to the metric. We're sticking with the gallons because we can easily see those things right away going away. If we expand this out, we have our negative 800 times the final minus the 40 degrees Celsius. That's going to equal to the 20,000 times, again, our final temperature minus our initial temperature. At this point, guys, it is algebra and keeping track of your negatives.
Shouldn't you
So
put
I
10 degrees
have
Celsius in as
negative. Oh, sorry. Thank you. Thank you. Sorry about that. Thank you.
Yeah.
So I have 800 TF. Negative times a negative is a positive. So positive 32,000 degrees C is equal to 20,000 TF minus 200,000. Just doing the math, we get 20,800 times TF is equal to 232,000 degrees C. Divide both sides by the 20,800. And our final temperature will equal 11.15 degrees C or 52 degrees Fahrenheit. Still too cold.
Depends on how much you want to swim.
Now, again, what we did here was nothing more than set up a system of equations. There, just one equation, one unknown. We're just looking for that final temperature, keeping very good track of our negative signs. And this is where I want you guys, you got to trust your math. You got to trust that you are keeping with yourself, because it looks kind of weird sometimes when you're first starting these problems to see, wait, I got a negative something here and these negatives, like, how are these all going to fall out? And trust me, it falls out. I have a question, but I don't want to interrupt you. Do it, Kimchi.
Okay. So the temperature final that you're finding is always going to be the same between the two because you're combining
Yes.
them, or is that not the case?
No, it'll always get there.
Okay, so yeah.
I mean, let's face it. I just dumped in some warm coffee into my cold coffee. Does that mean I'm going to drink through a cold area and then get to my hot, or my hot and then to my cold? Or does it pretty quickly get to the temperature it's going to get to?
Pretty quickly.
Yeah, pretty quickly. So we are not going to concern ourselves with what is called heat and mass transfer. I'm going to leave that to Tristan and Gherkin on their little chemical engineering side to worry about how do we maximize the transport of the hot molecules to the cold molecules to exchange their energy, and the time involved for them to actually do the physical heat transfer of the things. You and I are just going to assume we did it. We've let the requisite amount of time for them to sort it all out. What is the end product? The chemical engineers, and to a lesser extent the mechanicals, will worry about how to make that happen in a very quick or slow manner in order to extract the work that they want out of that system through heat exchangers and the like.
Mm-hmm. Would you ever
Does that make sense?
Yeah, this is kind of, I guess, not that important of a question, but would you ever try to get something to a certain temperature and then
Figure
make
out
it
how much stuff
stop,
to put in there?
like not have them be the same temperature in the end?
No, not for here.
Okay.
Not for here. Again, chemies and mechies, those guys will do things like that. Again, heat exchangers, the bread and butter for chemical engineers especially. You may want one stream to reach a certain temperature and another to not. Specifically, a week ago, I brewed beer. I had 100 Celsius beer coming down one tube. I had 0 Celsius ice water going up the opposite way. At the end of my copper tube, I had beer coming out at 23 Celsius, but my ice water was still 0 Celsius.
Mm-hmm.
What that tells me is that I did not allow them to get all the way to actual equilibrium.
Yeah.
I did not allow them to do that. If I wanted to do that, I would have made my tubing longer and said, great, you guys are all going to come out at like 21 Celsius. But I didn't want that. I still wanted that icy water so that I could continue to cool the beer as I pumped the water through. So I won't do that. when you go get your engineering degree, you're going to do that a lot. You're going to try to see at what point you reach the temperature that you want for one of your streams. Does that make sense?
Yeah.
Okay. Más preguntas. Did someone just leave the room here? I saw my thing shift around. Okay, now that we've done the trivial, which I'm doing just so that we can see the flow of heat from hot to cold, how do we do this? I want us to now do another one. Let's do this now with dissimilar. So this will show you how they each have their own heat capacities. Now with dissimilar materials. Okay, now I'm going to have to rely on some people to do some calculations for me here, because I have switched up my approach to this in conversations with my colleagues. When back in my day, I learned a lot of my stuff involving the NC delta T. So in the end, I would often have to take some sort of mass thing and convert it back down and do all that. In more recent conversations, it is apparently now much more common to be just shooting straight to the mass version of this. So the numbers that I have in my notes will not suffice for me. So I'm going to have to rely on you guys to give me good numbers. So here's the thing. Ooh, whimsical. All right. We're going to drop a 15-gram piece of copper at 85 degrees Celsius into 50 mils of water at 25 degrees Celsius. What will their final temp be?
Is that 1 milliliter?
Oh, sorry, 50. I said it and didn't write it. Thank you. Okay, so what does this look like? Oh, I love drawing pictures when I can. All right, so we have 50 mils of H2O at 25 degrees Celsius. Oh, copper's kind of an orangey. So I have 15 grams, and it is at 85 degrees Celsius, and I'm going to dump that in. At the end of the day, we have it in here. Question is, what is my final temperature? And since I know a couple of you guys are probably drawing that, I'm going to give you guys a second to look at that.
And so we're just ignoring like the containers in the atmosphere, right?
Yes, so I knew that you would do this to me, Dallas, and so I should have said it earlier. Oh, hells yes, are we going to ignore a ton of stuff? We are going to ignore heat losses to the atmosphere. We're going to ignore heat losses to the container they're in. We're going to ignore a whole bunch of that. That also includes the heat input, right? So let's say that glass were 25 degrees Celsius, but the room was 30. Well, the room would be pumping energy into that glass. So we are going to ignore a lot of stuff. If I didn't talk about it, you assume it's not happening. You want to start assuming it happens? Become a chemical engineer. We worry about that stuff left and right. The because all of those will contribute to either the heating up or cooling down of a system, and you have to account for them. When we talk about getting these delta H's, we will talk about something called a bomb calorimeter, and you can ask your question again there, Dallas, so that I can be very specific about what we're ignoring and why and how you could account for it if you didn't. Okay? Just say yes, Dallas.
Yeah. What about the CPs that?
Oh, I'm
We
giving
haven't
those
said
to you. Hold on. I'm just setting this thing up, man. Slow down. Not everyone's like just jumping on this like, I know what to do. All right, so what do we need to know about the copper? So the CP of copper, let me go look at my handy dandy chart. 0.385 joules per gram degrees Celsius or Kelvin, depending on what you want. And the heat capacity of water is 4.186 joules per mole degrees Celsius. By the way, I should go ahead and note that that's also 1 calorie. Hold on. It's, yeah, double check here. That shows for, let me make sure whether that's grams or moles before I do that. Since I'm doing the conversions in my brain, I don't want to do that. But essentially the 4.186 joules converts to a 1 calorie. Just in case you look some up somewhere and you're like, oh, but it's 1. Keep in mind your units. I think it's actually one calorie per mole C. But I'm not going to swear to it at the moment before I double check it.
1 calorie per gram.
It's 1 calorie per gram? Okay. Oh, actually, it's 4.186. Oh, that's why that works. It's not per mole. That's why my math wasn't working. I was like, why am I doing two conversions at once? It's 4.186 grams. I'm just looking at it again real quick. Want to make sure. Yeah, it's joules per gram. That's why it worked out. So there we go. So it is 1 calorie per gram degrees Celsius. So from calories to joules is 4.186. A lot of heat capacities will still be done in calories because that's where they were originally measured before we all switched to the metric. Okay, so let's take a look at our two systems. We have what is our copper doing and what is our water doing. Our copper is going to cool down, which is an MCP delta T. Our water is going to heat up, which is also an MCP delta T. Now again, the copper is cooling down, so that's going to be the negative. The water is going to be the positive. So we can say that the negative MCP delta T for the copper is equal to the positive MCP delta T for the water. And this is where it's going to get kind of fun because as I've worn that shirt before, it's just math. The trick here is, personally, I always like to solve things symbolically for as long as I can and then plug in all my numbers at the end so I don't screw something up with a transposition of a number or you name it. This is one of those situations where I don't do that. I will start calculating some numbers because it's going to be easier to keep track of those numbers than it is the variables in this situation. So on one side, I'm going to have negative the mass of the copper at 15 grams times its heat capacity, which I said was 0.385. Or 385 or 386? 5.
5.
And that's going to be joules per gram degrees Celsius. And I also have the temperature difference, which is final minus initial. So that final temperature minus the 85 degrees Celsius. This is going to be equal to the opposite over here. Now, what's the mass of my water?
50 grams.
And how did you do that?
50 milliliters times 1 gram per liter. 1 gram per milliliter.
That's right. So I'm just going to double check that so that everyone realizes that it is 1 gram per mil for water. And its heat capacity is 4.186 joules per gram degrees Celsius. And that is still going to be the final temperature minus the initial we said was
25 degrees
20.
Celsius.
Thank you, 25 Celsius. And so now I need some numbers calculated. Dallas, I need that 15 times 0.385, if you would.
5.775.
So we have negative 5.775. Notice that my units here, the grams, go away. Oops, sorry. Undo that. My grams go away. And this is now joules over degrees Celsius. I need you to now multiply that number by 85.
490.875.
490.9. And notice there that the Celsius will cancel and I'm left with just joules. Being very meticulous about my units here. Notice that I carried my negative sign through. That's why it's a positive 490. Dallas, give me 50 times 4.186.
209.3.
209.3. And this is joules per degree Celsius times our, oh, I forgot here. We needed our TF, sorry. Times our TF. And can you multiply that by 25?
Negative 5,232.5.
And that is now just joules because the Celsius would have canceled out. Does everyone see where those units are coming from and going? Does anyone not see it so I can point it out again? Everyone's okay? All right, hopefully you see that if I take my negative over to this side and my joules over to there, we're gonna get positives everywhere. So Dallas, if you can take 209.3 and add the 575 to it.
215.075.
So 215.1, I'll just go. It's okay, by the way, guys, to do some okay rounding here because a lot of it will come out in the wash. It usually shouldn't matter. Dallas, please do not go out 8 decimal places all the time unless you just want to hurt yourself. It's okay to start going like, okay, 075, we'll call that 1. That's going to be joules per degree Celsius times the final temperature. And Dallas, can you take the 5,000 and the 490, please?
5,723.38.
So I'm going to go with 0.4, and that is in joules. So what I'm going to do now is go ahead and just divide both sides by 215.1 joules per degree Celsius. 215.1 joules per degree Celsius. And what I want you to note here is that the joules per Celsius go away, and the joules go away. My Celsius now becomes my units. And so at the end of the day, Dallas will tell me that that final temperature is,
26.6 degrees Celsius.
and you know what I love about this?
It's barely any higher than the 25.
No, what I love about that is that's exactly what I have using other heat capacities and doing it in terms of moles and doing all sorts of other stuff. But guess what? Because you use your conversions correctly, because it doesn't actually matter as long as you play with your units, you must keep your units correct. I mean, I've harped on some of you guys for 3 semesters now. Units, 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 units. If you keep track of your units and do that, you will get it right. I had completely different units, completely different heat capacities in my old example. And guess what? I still got the same answer, and I should. Now, but yes, you're right, Dallas. I just want to point out that, yes, we have a 15 gram. So we're talking about the fact that the water is what? 3 times the amount of mass. Okay, 3 times the amount. And that copper being all super hot, 85 is really stinking hot, is still barely going to move that water because of this. Water has a heat capacity of 4, copper is 0.3. It takes 10 times the amount of energy to heat up the water. So yeah, I expect that temperature to barely move. That makes sense. It also makes sense because that number is in between the 2 numbers that we started with. Okay, that's important, because if it didn't, we would have a problem. If we suddenly said like, oh, it heated up to 90. Well, that's impossible because the copper was at 85 in the first place. It just doesn't make physical sense. You couldn't say that the final temperature were 23. It wouldn't make sense. So a couple of things that you can look at when doing these problems is, does it physically make sense? That's the nice thing about a lot of these thermodynamic problems we're going to do is, does it make sense? Does it make sense? You can physically start thinking about that. Okay, that's as far as I want to go today. Are there any questions about what we've been doing at all?
I did have one question.
Okay.
With regards to when you refer to certain the like backwards chemical reactions as, you know, it does not occur.
No, I'm not going to go there yet because we're not at the reaction stage yet. I only introduced it there. I don't want to talk about it for another couple of weeks, please.
All right.
We can talk about it in an office hour if you want, but I don't need it to start confusing things. We are not involving any chemical reactions right now. I need us to be very good at tracking the heat and how it flows, because when we get to actual chemical reactions, we'll be actually monitoring them because of the heat that they will transfer to, most often, a water system. And we need to be able to relate the heat that the water gains from the heat to the heat that the reaction gives off. And that will start telling us something about, did it want to do what it did or not? So right now we're just getting introduced to the idea that stuff goes from hot to cold. What does that mean for the final equilibrium, or, as we may see in another example, the initial startings of certain things? And then we will dovetail that into the energy of a reaction, which will dovetail into the Gibbs free energy of the reaction, and that's where we'll talk about, did you want to go or not? Right now, this has nothing to do with it, so I want to keep that out of our minds for a few weeks. Remember, this course builds and builds and builds.
What's dovetail?
Ask me in an office hour so I can pull up a bunch of pictures and show you. It's an expression you need to know, but basically means fitting into. But it has origins in woodworking. All right, if there are no more questions, I'm going to stop the recording.